Well, thanks everyone, and I appreciate the invite, Alex. And yeah, I love this subject, and like Alex was saying, most of my career I did gold exploration and production for various companies, and then say for the last 12 years, I pegmatites have always been kind of a passion for me, and always collected minerals from them, and did my master's on the tip-top pegmatite in South Dakota, and subsequently discovered three new minerals from there, and it just kind of continued on from there to the point where, in what I found is like in grad school, you learn the rudimentary aspects about pegmatites, and maybe if you're lucky, you get to go visit a pegmatite. And I ended up taking it to the next level by taking some trips to Brazil, and mainly because there were dealers down there that I knew from Tucson, and befriended them, and ended up going down there to visit them when I had switched commodities to iron ore. And then it just kind of became a yearly thing, and sometimes twice a year. And I most recently with the Arkenstone, up until the pandemic, I was going down there about twice a year. So it's been a lot of fun going to places that, I never thought I would when I was in either undergrad or grad school. So, took a little, a different path later on in the career. So anyway, yeah, that's what I'm going to talk about tonight. More specifically, how the pockets form in pegmatites, and how these, beautiful crystals like we see in the bottom of this slide here, how they form, and how do they survive, millions, sometimes even a billion or more years, in the earth. And then someone ends up finding a pegmatite and extracting these beautiful crystals. So, there's I guess there's a bit of romance there with this, and certainly a lot of interest. So that's what I based my talk on. So, before we get into this, there's some questions that I'm hoping to answer for us, and that is, what is a granite pegmatite? How do they form? What are the differences between a granite and its related pegmatites, as in chemistry, maybe texturally, mineralogy? What are some of the complex processes that form these gem-bearing pegmatites? And how old are they? They span a huge range. And what are the minerals that occur in them? And how common are pegmatite pockets? And, do the contents get preserved? And we know that some of them do, but we really don't know the extent. But I'll tell you a little bit. So to define granite pegmatites, they're totally crystalline, generally very coarse grained, light-colored igneous rock derived from apparent granite. And they're composed mostly of quartz, feldspar, and mica. And they differ in composition from a granite because they tend to be enriched in potassium, lithium, rubidium, cesium, fluorine, OH, and sometimes beryllium, niobium, tantalum, cesium, and tin. And, those are the interesting elements for me, because those are the ones that can form either gem crystals or very unusual rare species. And here's just for scale, a giant microcline crystal here, and this is at a road cut in Keystone, South Dakota. And my wife's there for scale, and I could tell you that she's 6'8", but I guess I'd be lying. She's 5'8". She did play basketball, but anyway. So that's her for scale. It gives you an idea, the size of, at least in this case, of a microcline crystal along this pegmatite road cut. And give you an indication of how big some of these crystals can be. So not more than 2 miles from this particular road cut is the Etta mine in the Black Hills. And that's where the largest spodumene in the world came from. And it was 14 meters long, okay? And there was a beryl crystal from Madagascar that was 18 meters long. So that kind of gives you perspective in terms of crystal size in these. So we know that pegmatites supply some of the nicest colored gemstones, you know, like tourmaline, topaz, and aquamarine, along with 40 other gem species. And these might be common to relatively rare species that they end up cutting for gemstones. And of course, they're also a great source for, you know, fantastic mineral specimens like some of the ones that I have pictured here. And they're a host to a diverse suite of minerals, and sometimes they're the only source of certain mineral species. To give you an idea, the picture there in the upper right is a specimen from the Tip-Top mine, and the white sheaves there are tip-topite, which is a complex sodium lithium phosphate. And then there's rocherite, beryllonite, todorokite, which is an oxide. And then a couple of the other species. So tip-topite was one of the ones that I discovered and co-described. There was also, I don't know if you're familiar with them or not, but pahasapaite and francileite, also unusual phosphates like this. But most of what we know them for is the fact that they're mined for economic concentration of rare elements. But these days, you know, not so much. The pegmatites in Brazil, they do try to recover as much, like columbite-tantalite, in some cases beryl, you know, for industrial purposes, and even cassiterite for tin. But it's just not as economic as some of the large-scale deposits of different kinds other than pegmatites that they're mining now, and even lithium. You know, they're going to saline brines rather than pegmatites for those. So bulk composition of a pegmatite is similar to a granite. They tend to have higher aluminum content, lower calcium content compared to granite. And the pegmatites that we're interested in, the miarolitic and the rare element pegmatites, they're often enriched in, like we said, lithium, beryllium, boron, fluorine, rubidium, cesium, and phosphorus, which is important for gem minerals and economic mining. And here's a photo of a pellucite with lepidolite out of my collection from Afghanistan. So the relationship to granites, they can be direct products of igneous fractionation from granitic melt. So what they really are is essentially quote unquote offspring of the granite parents. And we'll talk a little bit about that here in a bit. And then some kind may also have a metamorphic anatectic origin with no link to a parent granite. But most of the ones that we're going to talk about are the ones that are fractionation product from the granitic melt. And these diagrams kind of show you the distribution of the potential distribution of pegmatites around a granite, especially the one on the right. So I did a lot of my research on pegmatites in the Black Hills of South Dakota. And so, for example, that orange blob that's at the bottom of that would be the Harney Peak granite. And then what you see is, this is going vertically, so this is a cross section. You see different types of pegmatites that show different enrichments. So you have barren pegmatites essentially adjacent to or just outside of the margin of the granite. And then you have a series of pegmatites that might be enriched in beryllium, so they have a lot of beryl. And then it goes up to you know, boron, cesium, lithium, rubidium, and tantalum enrichment further away from the granite you go. And essentially, this sums up what I just said. The big thing here is that the more simple pegmatites are the ones that are more proximal to the granite, and the ones that are more highly fractionated are further away. So those are the ones that have cesium, lithium, rubidium, tantalum, and these rare element pegmatites, they intrude the country rock around the granite, as I said, and that is actually the most compelling argument for their genetic relationship from the granite to the pegmatite, and it's supported by geochemistry and age dating. So what do these things look like? The shapes of pegmatites are really variable. They can be dike-like, and in dike complexes, kind of like the Himalaya dike, pegmatite dike system in San Diego County, or they can be bulbous masses or inverted teardrop shapes, like the Black Hills. And then some of the factors, of course, that affect the shape are the kind of rocks that they intrude and the depth of their emplacement. So, the ones that are formed at depth tend to be those more bulbous masses, and the ones that are closer to the surface tend to be more dike-like. And a lot of this has to do with the structure of the host rock too. So if you're getting near surface and the fabric, whether it's schistosity or bedding in the rock, you have more of a tendency to form the dike-like pegmatites, and rather than the teardrop or odd-shaped pegmatites. And then there's also the differences between the lithostatic versus hydrostatic pressure. So the hydrostatic is the pressure that's essentially pushing these pegmatites up through the crust, and the lithostatic pressure is the pressure of the rock attempting to hold down the pegmatites, at least from rising through the crust. So give you an idea of size too. Some of you might be familiar with the Tanco pegmatite in Manitoba, which is really an amazing pegmatite, not only from its mineralogical diversity, but this is one of those pegmatites that is being mined economically, even to this day, mostly for cesium. And to give you an idea of the size here, this pegmatite is 1,400 meters long, so that's 1.4 kilometers. It's 600 meters wide and 100 meters thick. So it's huge. And you can see from this these longitudinal sections that they're pretty complex with respect to their zones or the distribution of the mineralogy. And I won't go into those in detail, but at least it gives you an idea. Compared to the photo at the right, which is the Helen Beryl pegmatite in Custer, near Custer, South Dakota. And this is kind of cool because you can see that they've actually mined out the core, which is where all the spodumene and the beryl, and there was part of a quartz core there too, where you found all of the tantalum mineralization. So, and this isn't very large. So, it's maybe 100 meters wide and maybe 150 meters tall. And this is one of those that's actually an inverted teardrop shape. So pegmatite classification, there have been early attempts like by Ginsberg, who put the classification related to depth. So, and then subsequent workers have modified that based on field work and geochemistry over the last 20 years. And Peter Cherney was one of the ones who really pioneered a lot of that. He was an amazing guy. And so as you can see here, these are kind of divided up just real quickly. The rare earth bearing pegmatites, both for the rare element and miarolitic pegmatites, they're in the NYF category. So the lithium, cesium, tantalum, LCT types, those are the ones that are largely in these the rare element and miarolitic ones that are in blue. So that tells you the main mineralogy that's in those. Just to give you an idea, and the ones, so in to go one step further in terms of deep versus shallow. So the deep ones, which they classify as these abyssal ones, so they're formed very deep in the crust, probably 12 kilometers or so. And the issue with those is that the lithostatic pressure is so high that you can't form cavities, pockets in the pegmatite. Okay, so most of the crystals that you find in those type are like frozen in quartz or feldspar. Okay, and they're not the ones that produce the gorgeous, usually the gorgeous gem crystals in pockets in pegmatite. So those are reserved for the rare element miarolitic pegmatites that are formed shallower in the crust. So I guess this is a question that if you're a mineral collector, right, like we are, do we want the one on the left where the tourmalines are frozen in the rock, or do we want the piece on the right where you have these gorgeous crystals of amazonite and albite and smoky quartz that are growing in these cavities, right? Sorry, I'm going for the one on the right, right? So, we talked about the unusual elements in the pegmatites, and you can kind of group those, these incompatible elements into what they call large ion lithophile elements. So these are ones that have pretty large atomic size and a relatively low charge. And then you have the high field strength elements where they have pretty small size and have a relatively high charge, okay? And it would be like, when I usually do this presentation, it's like comparing a basketball to a baseball, okay? And it's actually for that reason that both the size and the charge, that a lot of these elements, they get fractionated in the melt because they don't easily fit into like the feldspar structure, the micas, tourmaline, whatever, right? So they can't substitute into those. So they end up forming their own minerals, right? Which works for us because then you get, a lot of these unusual species in these gem pegmatites. And then of course, David London came up with this term, the pegmatophile elements, and that's lithium, beryllium, and boron. And again, those are ones that fractionate into the pegmatite, into the volatile phase. And yeah, I kind of customized this because what you get is with these pegmatites is you have kind of a pegmatite soup, right? And so you get all these unusual elements, these ones like cesium, lithium, rubidium that either have large size, low charge, or small size and high charge. And they end up forming their own minerals. And like in the upper left, there's a stibio-tantalite with elbaite. And then, of course, the boron goes into tourmaline, like the Malcon piece in the upper right. And then garnet, you can get some substitutions in garnet, and then some aquamarine there, bicolored aquamarine from Orongo. And this, I'm just going to throw this up here just for a little bit, but this gives you an idea of both the common and the more unusual mineral species that can be found in pegmatites. And like beryl, topaz, tourmaline, spessartine, spodumene, and less common ones like beryllonite, chrysoberyl, danburite, euclase, and the others, including petalite. And then also, you know, the trace elements, we like those too because they add variety in terms of color, like for tourmaline. So Mn3 plus gives you the pink zones in tourmaline, Fe2 plus the green zones, and copper, like in the Paraíba tourmalines, gives it the blue-green. So this is kind of what I'm talking about as far as fractionation. This is a good diagram from London's PEGMATITE book. And so the box on the lower left, it shows you the, as an example, the concentration of some of these elements in the granite. So you're talking about 20 parts per million lithium, 3 ppm cesium, and so on. You know, you can read that. And then when it comes to the pegmatite phase, when you get the fractionation in the volatile phase, in the pegmatite portion, these elements can be enriched anywhere from 2 times to 1,000 times the concentration that they were in the granite, and it's because of the volatile component in the melt that forms the pegmatite. So what does this volatile enrichment do? Well, it increases the polymerization in the melt. It decreases the viscosity, decreases the solidus temperatures, decreases the nucleation rate, increases rates of diffusion, and increases solubility. And this is all good because what it does is that they essentially serve as a flux in this melt, in this volatile rich melt, and it helps form large crystals and the gem crystals. And here's another example, and this one's from the Bumpus Quarry in Maine. And as I mentioned too, that beryl from Madagascar, the one that was 18 meters in length, it was 3.5 meters in diameter and had a mass of 419 tons, just to give you an idea. And that size is enabled by the role of the volatiles in the pegmatite, you know, enabling these anions and cations to move around easily and form these large crystals. And ultimately, I'll just go through some of these. When we talk about lowering the temperature of crystallization, so some of these minerals are actually able to form at less than 350 degrees centigrade. Okay, so you're dropping it from, say, typically at 650 degrees C down to 350 degrees centigrade in the pegmatite melt. And again, this helps to produce these gem-bearing crystals. And the reason we know this is that a lot of the experimental work that Dave London, Karen Weber, and many others have done have really shown this. And this is really cutting edge work over the last decade, maybe a little more, that they're finding this out. Because, you know, historically, you know, a lot of times we hear too that, like, pegmatites, the reason they have large crystals is because they take a long time to form, right? Well, that may not be the case, and it probably isn't the case, as they're finding out. So, and that's where we'll get into this in terms of rates of crystallization. In terms of the recent work that, like, London and Weber and others have done, they're thinking like days to months, or maybe decades to hundreds of years for some of these pegmatites to form. And then, of course, the thin dikes, you know, like those in maybe the Pala district in California, and those in Pakistan and Afghanistan, those might form more quickly than some of the big bulbous masses probably like the Tanco pegmatite and certainly the ones in the Black Hills. So as far as pegmatite anatomy goes, so, you know, what do these things look like? You know, some of them are very simple. They don't show any zoning. Like I've shown here on the diagram at the right, and this is a zone pegmatite, and they go from a core zone, and then you have an intermediate zone, a wall zone, and a border zone. And this is kind of simplified because you can actually have, especially as far as the intermediate zone goes, you can have multiple intermediate zones. So in most shallow through intermediate depth pegmatite tites, they really do show this internal structure. And then you also get these replacement bodies and fracture fillings, and that makes life interesting in the pegmatite, and it also helps with a lot of the unusual species and the unusual textures we can see in some pegmatites. So what happens here is, if you look at this diagram on the right, so the wall zone and the border zone cool, and then you get crystallization inwards, or cooling as you go inwards with crystallization. And then maybe at some point, whether it's tectonic, there's some tectonic forces going on, or you just get shrinkage of the pegmatite a little bit from cooling, right? And so what happens is you get these fractures that transect the pegmatite, and it might go from the core or maybe one of the intermediate zones, and then it will transgress and go out into the other zones. And sometimes, you know, it will go through fractures, or it will just permeate the rock through diffusion, and you might get this metasomatism like that's shown in green. And so you get alteration, and that's where you get replacement of pre-existing minerals like muscovite replacing elbaite, and unusual things. And then sometimes too, you might have beryl crystals, in this case, say, where they're acted upon by these late stage fractures in the fluids, and they alter to like bertrandite or maybe some of those bizarre secondary phosphates. So the complex pegmatites, they're zoned. They have fracture filling and or replacement units. They tend to have higher concentrations of boron, lithium, phosphorus, fluorine, and water, along with beryllium, niobium, tantalum, cesium, and tin. And they're formed from these highly evolved volatile-rich melts that, of course, produce these pockets that have these gorgeous gem crystals in them. And you know, I kind of wanted to show you part of my collection, but I'm kind of doing the next best thing. So this might be hard to see, but here's a good example. And this is albite and schorl with a big gemmy aquamarine crystal. And so this came out of a miarolitic cavity in a pegmatite in Pakistan. Okay, so that's almost as good as being there. So so that's what we're talking about in these pockets. And the miarolitic pegmatites, so they form between, say, less than 1.5 kilometers and 3.5 kilometers of depth. They have pockets or cavities with gem crystals, and these can be located in the upper parts of the parent granite and in the adjacent host rock. And of course, they commonly contain minerals like we just saw. So you can have aquamarine, quartz, tourmaline, topaz, and feldspars like the albite, along with layer silicates, you know, whether it's muscovite, the petalite, whatever, and along with other mineral species. So as far as the mineralogy goes, they're dominated by silicates, phosphates, and oxides. And of course, the most common silicates are quartz, microcline, feldspar, albite, and muscovite. And then spodumene, beryl, topaz, tourmaline, and usually spessartine garnet are common in some pegmatites. And here's some examples of some silicates. So we've got spessartine on the left, big elbaite on a, almost looks like some type of an albite snowman. And this thing is huge. That piece is probably half a meter tall, so it's a big piece. And then the petalite crystal on the right. And here's some more silicates: a heliodor from the Ukraine, aquamarine from Brazil, and a beautiful cherry-colored topaz from Pakistan. And then we have the oxides like columbite-tantalite, cassiterite, chrysoberyl, and wodginite. And so I got to tell you a little story about the wodginite on the right. So that's out of my collection. That was from one of my trips to Brazil. And it was really interesting because they were mining and stockpiling this both for specimens and for, tantalum ore, right? And so I go down there, and I knew the family that owned this pegmatite, and they didn't really know what this was. They thought it was, columbite-tantalite, part of that series. And I looked at it, and nope, wrong crystal form. And I thought it was wodginite, and yep, sure enough, we did the analyses. And so I ended up buying up a half a dozen of these, and they were anywhere from, this piece is probably almost a kilogram, the one on the right, and up to pieces that were several kilograms. Okay, and we had these shipped up here. Yeah, and they're probably some of the largest and finest wodginite crystals that we're aware of. And then you have the phosphates like fluorapatite on the left, and monobrassite, and its other end member, amblygonite. And then you have halides and borates. So you can get fluorite in pegmatites. It's not uncommon, especially from Pakistan and Afghanistan. And then oddballs like this beryllonite, sciavinitoite from Madagascar, and those are tantalum and or niobium borates. So I just love the diversity. And some people are really shocked when I tell them that zeolites can be found in pegmatites. And yeah, at late stage, low temperatures, you have the same elements available at the late stage too. So you can have sodium, calcium, potassium, and other cations and to form these aluminosilicates that contain a bit of water, and like the Himalaya dike system, it's uncommon, but there's quite a bit of stilbite that can be found in that system, at least historically. And then this piece on the right is one that I acquired from an Afghani dealer in Tucson, and he had no idea what the minerals were on this. He knew where it was from, but he didn't know what the minerals were. And of course, I kind of talked around it and said I wasn't sure, but I'd find out, but I'd like to buy the piece, right? And yeah, it turned out to be, I knew it was hewlandite, and I figured it was probably bavenite, but I had the bavenite confirmed. So interesting things, whether you're at shows or out in the field. So as far as the gem pockets go, that residual melt accumulates, and you get this low density, volatile rich liquid that exalts that has all these rare elements in it. and then the pegmatite starts crystallizing from the wall, from the contact to the core, and then the pockets are some of the last features to form during crystallization, and those are the ones that are important for producing gem minerals. And these pockets, as far as size, they can be like a few meters to several meters in size. You can walk in. And it's kind of fun when I went down to Brazil and I visited this one family-owned pegmatite down there. And I got to tell you, it was kind of crazy because the way you got down into the pegmatite, and I've got a picture of it later, they had a gasoline-powered winch that was hooked to a cable with a log on the end, and you straddled the log and the cable, and that's how you went down like 100 feet into this pegmatite. And you got down there, and then all you see is all these big open pockets, but they didn't have much left because they had mined it all out. But they had mined tourmaline quartz, lepidolite, for the most part, and then some really nice rose quartz. So it just gives you the idea of you know, how big these things are. And I walked into them. I mean, they were probably 2 meters tall by 3 meters wide by maybe 6 meters long. So they're pretty large. And so these gem pockets, they're generally found at the intermediate core margin. The core is usually massive quartz, maybe with a little bit of spodumene and some tantalum niobium oxides, but not many pockets in the core. And they're abundant in the shallow pegmatites, but they're absent in the deeper, higher pressure environments, like I was talking earlier. And you know, one thing I kind of like to show for this, and it's tough to do it here, but it's like if you take a tall glass and you pour 7-Up into it, and you look at the bubbles when you do this. Yeah, ginger ale, whatever. You'll never look at a glass of soda again the same. But the bubbles way at the bottom of the glass are tiny, right? And as the bubbles start to go up toward the top of the glass and make their way up through the soda, they get larger. So that's the same thing that's going on with these pegmatites, the ones at depth, too high a lithostatic pressure to form pockets. So they're tight. The crystals are frozen in the rock. And then by the time you get near the surface, much lower pressure, so you're able to form these. I'm not going to. They're gas gel pockets that end up crystallizing these beautiful minerals. Okay, so we kind of went through this already, but so like the pocket-bearing pegmatites might be pretty pervasive in certain pegmatite regions, like the ones in Brazil, Pakistan, Afghanistan, the ones in Southern California. But you know, still these cavities are still not common in them, right? It's not like these things are just everywhere. You run into a lot of barren rock before you find a pocket. Okay, and the ones that have like gem tourmaline, aquamarine, kunzite, you know, crystals of kunzite like this, they're even more rare. Okay, so I'm trying to give you an idea of you know, how uncommon these big, beautiful gem crystals are. It's not like they're found all the time, and they're not available everywhere. You know that from going to shows, you know, especially for really good pieces like the ones I've shown you here. So pockets are rare. Pockets containing preserved gem crystals are what I think almost a miracle. And here's a diagram that Wendell Wilson put together for the Jonas pegmatite. And this is actually sort of a cartoonish reconstruction, but he actually, from pieces that were collected from the pegmatite and from some of the miners that mined that pegmatite, that's what his illustration is based on. And it's a pretty amazing diagram, really. And then on the right, that's an example of a tabular albite crystal from the Jonas pocket. Okay, pocket distribution in pegmatites is erratic, and their location can be very difficult to almost impossible to predict. They vary in size and shape within a pegmatite, and there's no relationship between the size of the pegmatite to the size and shape of the pockets. And the mineralogy of one pocket to another can vary significantly. So I've been in pegmatites in Brazil where you have a pocket over here that has tourmaline and beryl in it with good maybe microcline and a little bit of lepidolite, and they end up finding a pocket, say a few meters away, might be much larger, and it's full of these huge quartz crystals, maybe with just a little bit of tourmaline and then muscovite and whatnot, right? So the real disparity, and you can imagine the frustration of the miners, you know, when they're trying to locate these things, and they get excited when they hit a pocket, and sure, you know, they can mine these giant quartz crystals out, and they can make a profit on those. But then, you know, they're looking for the beryl crystals or tourmaline crystals, and they could spend months trying to mine and get the right direction to the next pocket. And then when they hit it, yeah, it might be fabulous with great tourmalines and beryls and topaz. So it's kind of hit or miss, and there's a bit of risk involved. Okay, pocket crystals are dominated by feldspars, quartz, and micas, generally rooted in the margins of the pocket, in that particular pocket. And they're generally a lot larger than the later form gem crystals. And then you have other species that end up growing maybe at a little bit later stage that form in the pocket too. And so it gives you this complex paragenesis where you have like quartz and tourmaline, like on the photo on the right, you have that growing in the pocket. And then maybe later on at a later stage, you know, you get a later pulse of phosphate in there. So you might get like an amblygonite or a monobrassite crystal, maybe perched on those earlier formed quartz and feldspars. And this is one of my favorite pieces that Carl Warning has from one of Alex and my colleagues here. And this is just a beautiful piece from Spagnala. And I hope the colors come through because it's just gorgeous the way it's zoned from like an olive green at the base to almost a whitish zone near the top, and then a rich pink at the terminations. And then you have, you can potentially have pocket rupture too, maybe because of high fluid pressure in the pocket, or you get some of that tectonic activity I was talking about, or maybe just shrinkage in the pegmatite, right? And so you get, you have these pre-existing crystals, these beautiful crystals, feldspars, quartz, tourmalines, whatever, and if the pocket ruptures, then that's where you get a lot of these crystals. They break off and you end up finding them in the bottom of the pocket when the pocket's discovered, along with a lot of maybe clay that fills the pocket, right? So it's one of those things where, yeah, like at the Himalaya, it's great when they found these clay-filled pockets, even though the crystals were broken, you know, you still had great singles that came out of it. And it's even more special when you don't have pocket rupture and the crystals are intact. Alteration in late stage fluids, I kind of talked a little bit about this earlier. So yeah, during late stages of crystallization, you know, you might get the phosphate along with beryllium and lithium, sodium and whatnot, and you end up forming these beautiful minerals like this one, and this is a beryllonite, crystal on a hydroxyl herderite from Pakistan. And so, you know, these make it interesting too. So ideal pocket condition or formation summary, you have to have enough volatiles and favorable pressure environment. The volatiles promote diffusion and limit nucleation, resulting in larger, well-formed crystals. And the crystals grow into the open space, which, and I need to keep qualifying this. So it's not like it's air. So the crystals are growing into a fluid or gel-filled cavity, okay? And that's how they form. And later on, what happens to that fluid or that gel, it can either escape through fractures in the cavity, or sometimes it gels and forms the clay-filled pocket. So it might just form kaolinite and hopefully preserve the contents. So you have complex fluid chemistry and complex paragenesis, and then maybe you have pocket rupture by internal pegmatite adjustments or tectonic movements, and then maybe even filling with clay that could preserve or protect the pocket. So ages, they range in age from, say, less than 35 million years to 3.5 billion years. And to give you an example, the Afghan Pakistan pegmatites, they're pretty young, about 35 million years. Even the California pegmatites aren't all that old, about 100 million. And then the Orongo pegmatites, similar, about 130 million. The Chinese pegmatites in the northern Altai province, about 220. And then the Brazilian pegmatites in the Brazilian pegmatite province, they're about 500 million years old. And then you get the ones in the Ukraine and the ones in the Black Hills that are 1.7 billion years old. Okay, and what I find amazing about those Ukraine chamber pegmatites is that they're 1.7 billion years old, and so many of them still have open space in them, and it was preserved. And you know, you get those beautiful heliodors. Okay, and here's some statistics for you. Less than 1% of all pegmatites are miarolitic or have pockets. And less than 1% of these contain gem crystals in well-crystallized rare and unusual species. And then less than 1% of the gem crystal pockets survive intact. So that's why I say it's kind of a miracle that we even get pieces like this to acquire and display in our collections, right? And here's some examples of preservation and extraction. And you know, that's the other part of it too, right? So, you know, these beautiful specimens, yeah, they have to survive the whole process of pegmatite formation and geologic time until someone discovers the pegmatite and the cavities that are in them. And then, you know, then it's the skill of that person to extract these beautiful pieces, right? I mean, there's a special skill set involved in taking these things out. And, you know, I'll give you an example. And, you know, I got to hand it to Bill Larson. You know, he really kind of perfected collecting techniques in pegmatite at the Himalaya mine and where he mined. And like on the other extreme, the other thing that I find, like when I go to Brazil, some of the Brazilian miners, they're very anxious to turn a profit, right? So that's when they might be motivated. They don't care if they're on matrix, right? So they just go in and they start breaking crystals off the matrix, and you have lots of singles, right? So, and that's difficult for me. I understand their situation, but I mean, I've gone to offices of some of these pegmatite owners, And it's almost sickening when they bring out a bag, right? And they dump all these tourmaline crystals out onto the table, right? And yeah, you can pick through and find some nice pieces, but so many of them have damage. And, you know, that's a little bit of headway that I was trying to make on my trips to Brazil is you talk with these mine owners and say, okay, you know, you mine this pocket and you mine it quickly. And sure, maybe you make $100,000 on all of these single tourmaline crystals after you sell them all, right? Or do you want to make 10 times that if you attempt to extract them and preserve them with matrix, right? At least to some extent. So it's a tough thing. And, you know, the same thing happens in Pakistan and Afghanistan, but they're also getting much better at specimen extraction. And so in these two pieces are just amazing, you know. Yes, they were extracted. Yes, they were in pieces when they were found. And then the other miracle is that there are people out there who have the skill set, kind of like the jigsaw puzzle, right? To put these things back together again, right? And some of these, I don't know how many, you know, repairs there are in these two, but, you know, probably several, but, you know, at least these pieces were preserved. So here's some other products of preservation and extraction. And this is kind of a summary of the life of a gem crystal. So they have to outlast the pegmatite and the pocket forming process. They have to survive the late stage equilibration and fracturing of the pocket, you know, rupturing, etching, dissolution, alteration, whatever. And then there's the waiting process, what I call the waiting process. Will it outlast geologic time? I mean, millions of years or maybe even 1.7 billion years before they're discovered, right? And then will it survive discovery and extraction? And then, you know, after you collect these things, you know, you have to, as any field collector, I'm sure there's plenty of field collectors that are watching this, you know, it's this, it's the packaging, it's the careful packaging and the transportation of these, right? So that these things can come back relatively intact. And then they have to persist through the laboratory prep work. And then ultimately, you know, end up on display in someone's collection. And these are just some photographs. So this picture at the bottom here, yeah, that's the one I was telling you about, where I'm getting winched down on a log into this pegmatite on a gas-powered winch. And yeah, it was interesting. And then this is very common in more advanced recovery techniques, is using a diamond edge chainsaw to recover specimens. And here's some very accomplished pegmatite miners and preservers of some great specimens. So in summary, gem-bearing and rare element pegmatites are fractionation processes, products of the parent granite. They're enriched in incompatible elements and volatiles that enable the formation of giant crystals, as well as pocket and gem crystals, if they're placed at shallower levels. Gem-bearing pegmatites, as far as their age, can be anywhere from 35 million to 3.5 billion years old. They have diverse mineralogy that goes all the way from the sulfide group to the silicate group. And pegmatite pockets, like we mentioned, they're rare, and finding a pocket is mostly intact is it really is almost a miracle. And then finding and extracting gem crystals from a pocket for collectors is definitely an art. So I guess what I'd like to say, just in closing, is that granite pegmatites are an intriguing igneous rock and mineral deposit type. And they represent an unusual combination of common and rare elements that combine to form a diverse and beautiful assemblage of minerals, potentially with complex paragenesis. And I study and collect pegmatite minerals for these reasons, and because to me, you know, their artistry is manifested in a lot of different ways, not just in their outward appearance. So I like the ones that are beautiful, you know, like the tourmalines, the spodumines, aquamarines, but I like the rare species too, like, you know, beryllonite, brazilianite, all those. And, you know, a lot of it and most of it is for all of the great people that I meet on the way. Just wonderful peoples, whether it's collectors, you know, the miners. It's one of the reasons why I collect.